Folks, got another interesting problem for you here. We're looking for all positive integers. I've seen it called Z plus occasionally, Z plus, Z superscript plus, or N. There's some debate about whether N involves 0 or not, so this is 0. This rules out the possibility of 0. Now we're looking for all N such that 3 times the quantity N squared plus 1 is a square integer. And it's a good problem probably to do some discovery on. I've done some of the computations here for you. None of these are k squared, right? Okay, and all I did was check the first 7 here, and you guys can verify. I'm pretty sure I got the arithmetic correct. I just noticed right here, if you try 8, that would give you 3 times 65, right? Let's see, what's that, 195? Oh, this is close. Okay, but no cigar on this one. This is 195, right, if I'm doing my computation. And notice that 14 squared is 196. So we got close right here. But it didn't work for the first 8 trials. That still doesn't mean anything. That doesn't mean there's not one out there. So let's look at the general approach here. Now, so what I'm going to do is just assume that there is such of k. I'd set our expression equal to k squared. And I think it's important to state this existentially, that this is for some n and k, some specific n and k. I could put that backwards e symbol right here, so you wouldn't necessarily think it was just the original free ranging variables at the beginning. So this actually says, suppose it happens for a particular n and k. Some people will subscript these letters or call them something else. But anyway, this is specific enough, I think. Okay. Now, this is fairly routine. This problem right here is true. The only way that k squared can be a multiple of 3 is if k is equal to 3m for some m, some positive integer m, right? That's the only way that can possibly happen. And so that gives us a little bit of a break right here, because what we have here is n squared plus 1 is equal to 3m. Now notice 3m squared. Now notice this piece right here is always congruent to 0 mod 3 without even having to check m. Right? So the right-hand side is a constant in modulo arithmetic, namely 0. Now, you guys may have seen the result, k squared, and this is you could just prove it right in your head immediately. K squared is congruent. Any integer squared is either 0 or 1. And we're doing mod 3, of course, mod 3. All right, and again, the way to check that, all you got to do is check 0, 1, and 2. When you check 2, you get 2 squared is 4, which is also congruent to 1, right? Now, you'll notice that means that this piece over here would have to be either 1 or 2 mod 3. Okay, if you check n equals 0, 1, and 2, well, you don't really have to do that because you already know that k squared is 0 or 1 mod 2. But anyway, this would mean that this guy right here is congruent to 1 or 2, and again, it's mod 3. So you see, we got a contradiction here. This is impossible. Okay, impossible. And so there are none. Again, this is certainly true. This is incontrovertibly true right here. And then all of this analysis in mod 3 makes it very clear that this cannot occur. If we set it equal to an integer squared, we get an impossibility. So it says find all n, there are none. It's the empty set, okay? I don't know if it's proper to write this as n as a member of the empty set, but there are no solutions in for this possible. I mean, it came close right here at 195. Right, but that's not going to get it. Okay, it'd be interesting to see how many came within 1. But anyway, we're done. Impossible QED, I guess.